A new study based on radar experiment data from the Cassini-Huygens mission to Saturn has revealed new insights about the structure and activity of the liquid hydrocarbon seas near Titan's North Pole, Saturn's largest moon, which boasts 146 known moons. A research team led by Cornell University analyzed data from various bistatic radar experiments to separately examine and estimate the composition and roughness of Titan's sea surfaces, an achievement that previous analyses using monostatic radar data had not accomplished. This approach will aid in future combined analyses of Titan's seas using Cassini data. Valerio Poggiali, a research associate at Cornell University, is the lead author of the study titled Surface Properties of Titan's Seas Revealed by Cassini Mission Bistatic Radar Experiments, published on July 16 in Nature Communications. A bistatic radar experiment involves directing a radio beam from the spacecraft towards a target, in this case Titan, to reflect it back to a receiving antenna on Earth. This surface reflection is polarized, providing information from two independent perspectives, unlike monostatic radar data, where the reflected signal returns to the spacecraft. Poggiali explains that the primary difference lies in bistatic information being a more complete data set, sensitive to both the composition and roughness of the reflecting surface. The current study utilized 4 bistatic radar observations collected by Cassini during 4 flybys in 2014, May 17th, June 18th, October 24th, and 2016, November 14th. During each flyby, surface reflections were observed as the spacecraft approached and receded from Titan. The team analyzed data from the exit observations of Titan's 3 large polar seas, Kraken Mare, Ligeia Mare, and Punga Mare. Their analysis found variations in the composition of the hydrocarbon sea's surface layers, depending on latitude and location, such as proximity to rivers and estuaries. Specifically, the southernmost part of Kraken Mare exhibited the highest dielectric constant, a measure of a material's ability to reflect radio signals. For example, water on Earth is highly reflective, with a dielectric constant of about 80, while Titan's ethane and methane seas are around 1.7. Researchers also determined that during the flybys, all 3 seas were mostly calm, with surface waves no larger than 3.3 millimeters. Slightly higher roughness levels, up to 5.2 millimeter, were detected near coastal areas, estuaries, and straits between basins, indicating possible tidal currents. We have indications that the rivers feeding into the seas are nearly pure methane until they reach the open liquid seas, which are richer in ethane, Poggiali said, likening it to how freshwater rivers on Earth flow into and mix with the salty waters of oceans. This fits well with Titan's meteorological models, noted co-author and astronomy professor Philip Nicholson. We expect that the rain falling from the skies is likely almost pure methane, but contains trace amounts of ethane and other hydrocarbons, he explained. Poggiali mentioned that further analysis of the data generated during Cassini's 13-year study of Titan is ongoing. There is a wealth of data waiting to be fully analyzed that will provide even more discoveries, he said. This is just the first step,